Now we're going to look at rational functions and limits. We've talked about rational functions and their features, their wholes and their asymptotes, and horizontal and vertical asymptotes, what happens as x goes to infinity, and all sorts of things like that. And all of those things can be described using limit vocabulary. So first of all, we're going to look what happens as x goes to infinity. And so if we look at this graph right here, we can see as x goes to infinity, so let's just actually draw in that as x goes to infinity here, to positive infinity, or to negative infinity, is for that matter. Notice what's happening to y. Y is also going to infinity. And we see this from our function here. We notice that the numerator has the higher degree. Degree of numerator is higher than the degree of the denominator. When the degree of the numerator is higher, we know that as x goes to infinity, y goes to infinity. So I'm just going to say the limit as x goes to infinity of this function is infinity. Or we say the limit as x goes to infinity is infinite. Now, when a limit goes to infinity, we say the limit does not exist, because a limit means that you have a limiting value. It stops at some point. There is no stopping at this graph. It just keeps going. So there is no limit. In this case, however, we do have a way to find an asymptote. So this just is a review. We take the numerator and we divide it by the denominator whenever we have the larger degree in the numerator. And what we get when we divide is our asymptote, or the graph. If it divides evenly, it's actually the graph with a hole in it. So when we take the numerator and divide it by the denominator, in this case, we have an x cubed divided by an x. So an x cubed divided by x gives me x squared. So the asymptote is actually parabolic. So if I were to sketch in the asymptote here, it actually looks like this. And then we also have a vertical asymptote here, and so you can see how the graph fits in between the asymptotes. Kind of an interesting graph. I hadn't shown you one like that before. Okay, the second example is when the degree of the denominator is higher than the degree of the numerator. So when the denominator is increasingly getting bigger and bigger faster than the numerator, you know that the graph levels off to 0. So we say the limit is equal to 0, and that's this asymptote right here. We also have two vertical asymptotes I can draw in, which we'll talk about later, how those are related to limits. So we say the limit exists in this case. The limit exists, and the asymptote is a horizontal line at y equals 0. So you can see that when we take x to infinity and the limit exists, we actually get a horizontal asymptote here. I think I have a horizontal asymptote rather than a horizontal. Some of you are screaming about that right now, so let me correct my spelling. Okay, the degree of the numerator is equal to the degree of the denominator. When the two are equal, we're looking at these, we see that in the long run, as x goes to infinity, the graph is going to level off to just be 3. So here we have a horizontal asymptote at 3. We also have two vertical asymptotes, you can see, which create the shape of this graph. So once again, the limit exists, and the asymptote is a horizontal, spelled correctly this time, line at y equals 3, at y equals 3. So there is both a limit, and it's also the feature on the graph that we see is the horizontal asymptote. And we saw that on a previous page when we were looking at an exponential function. It also had a horizontal asymptote at 0, and so its limit as x went to negative infinity at least was 0. Now we're going to lead into now what happens when x goes to a particular number rather than to infinity. And the formal definition of a limit says this, and I need to get this to go up. Sorry, I'm having a little trouble with my scroll bar. There we go. L is the limit as x goes to the number c of the function f of x if and only if you can keep f of x arbitrarily close to L. In other words, keep y close to the limit L by keeping x sufficiently close enough to c but not equal to c. In other words, if you plug a number very, very close to c into the function, so if our x is very, very close to c, we would get a number very, very close to L. In other words, our y value would get close to L. And if we get closer to c, y gets closer to L. So we're going to look at that with a pretty simple example. We're going to look at just a regular parabola. No gaps, no holes, no asymptotes, nothing. Just a regular parabola. And we're going to say, what is the limit as x approaches -1? Now, I'm not going to start by putting -1 into the function. I'm going to start by putting something close to -1 into the function. So we're going to look at a graph here of this function. I have it in trace mode. So if I type in something close to -1, like -1.001. Okay, move my little recording icon. Actually, apparently rounded it to, let's see if I can change my settings here. I'm going to pause for a sec. Okay, I changed my settings to show more decimal places so that I could actually do this example a little better. Notice, I'm going to go to trace again. If I type in -1.001, you will see that at the bottom of the screen, you'll see that y is equal to 5.004. Now, what the limit theory says that is, if I get closer to -1, that my y value should get closer to whatever the limit is. It looks as if the limit is 5. So if we type in -1 point, oops, I don't think I got the 1 in there, -1.0001, it looks like I got a little bit closer because I got 5.0004. Now if I type in something less than negative, or a little greater than -1, like -0.99, notice I get 4.9601. If I put -0.999, which is closer to -1, I get 0.49996. -0.99999. Notice I'm getting really, really close to 5 now, 4.99996. If I put in enough decimal places, it will just round it to 5. But let's actually put in -1 here. Put in -1, I get 5. Now what am I trying to prove here? I'm just trying to show you what the definition of this limit is. What if x is very close to but less than -1? So we get close to -5. I'm sorry, close to +5. We get close to 5. And on the other, and if x is very close to but greater than -1, we got, so this was close to 5 and this was greater than 5. This was close to 5 and it was less than 5. And we also noticed that as we got closer to -1 on either side, we got closer to 5. So this fits the definition that we can keep our L value, our limit, close to the actual limit by keeping x sufficiently close to 3, in this case, to c. In this case, c is -1. So by keeping x sufficiently close to -1, I can keep y sufficiently close to my limit L. I can keep it within it gets closer and closer. So here we say the limit as x approaches -1 is 5. Because when we plug this number in, we get 5. -1 squared minus 2 times -1 plus 2 is actually equal to 5. That means that -1, 5 is a point on the graph. And that the graph is continuous at x equal -1. So if I can just plug that number in and I plug in a value for x and I get a value for y, and whenever I get close to my x value, I get close to that same y value, that means there is no hole, there is no gap, it's just a point on the graph. So this is what I kind of think of as sort of the boring limit, because it really isn't difficult to find, and it's really kind of what you might think is almost pointless to find. But this is basically illustrating the definition of a limit. As I get really close to -1 as I really blah 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 blah, as x gets very, very close to -1, y gets very, very close to 5. And the closer I get to -1 for x, the closer I get to 5 for y. So the limit is 5 as x approaches -1. Now we're going to get to a little more interesting ones. What if, when at a certain number, in this case 3, what if there is nothing there? What if, you can see here, if I look at this graph, that there's a vertical asymptote at 3. And you can see from here why that vertical asymptote is there, because if x is equal to 3, this function is undefined. So I actually have a vertical asymptote. And we can see what happens to y as we're getting close to 3 is it's either going to positive infinity or it's going to negative infinity. Okay, so the closer I get to 3, what happens to y? So let's just look at this graph. I've got this graph also on here. Find where it is. So we'll trace. Here's this graph. So if we put in a value, if we put in 3 first of all, let me get this out of the way again. If we put in 3, you'll notice that it's undefined at 3. If we put in something close to 3, like 2.9, notice I get -5.39. Okay, it's actually right there on, oh, every time I move my cursor, things change. I won't move my cursor. But when I put in 2.9, I get -5.39. If I put in something closer to 3, 2.99, I get -95. If I put in 2.999, I get -995. If I put 2.99999, I get -999,995. So as x is getting closer to 3, y isn't getting closer to anything, it's getting farther away from anything. It's getting bigger and bigger in the negative direction. Now if I put in something close to 3 in the positive direction, like 3.1, I get 15.41. If I put in 3.01, which is closer to 3, 105. 3.0001, 10,005, and so forth. 3.000001. One more. I have 1 times 10 to the 8th, which would be about 100 million, I believe, at that point. So you see here, and I'm going to reset this. Escape, menu. Let's go back to what basic graph. That isn't exactly what I wanted it to look like to start out with. Let me move it. There we go. Kind of see what it looks like. It's always nice to be able to return to my original settings to some extent. Okay, that looks a little better. There we go. You can see that as x goes to as x approaches 3 from either the left or the right or the left, y isn't approaching anything. Y is getting farther away from things. This is known as an infinite limit. So if we were to plug in 3 into the numerator, let's put 3 into the numerator. We get 27 minus 5 times 9 plus 24 minus 5. And in the denominator, we get 3 minus 3, which is 0. In the numerator, let's see, this is -45, -50, +51. We get 1 over 0. Whenever you see a non-zero number in the numerator and 0 in the denominator, that tells me I have a vertical asymptote. That tells me that I have the limit is infinite. So L equals the limit of x goes to 3 of f of x is infinity. So we have basically from both sides, positive and negative infinity, we have no limit exists as x gets closer to 3, y gets infinitely big. It doesn't approach anything. Y doesn't get close to anything. And because of that, we have no limit, and we know that that has to be a vertical asymptote. Now let's see what happens here. We have a very similar graph now, but it has a hole in it, and we have a very similar equation. Let's see what happens if we plug in a value, the limit, into the function as x gets close to 3. So what happens? We get 27 minus 5 times 9 plus 24 minus 6 all over 3 minus 3. Well, if you can compute the numerator, I have 27 and 24 is 51, and then I have negative 45 and a negative 6, which is negative 51, so I end up with 0 in the numerator, 0 in the denominator. Whenever you get 0 over 0, this means you're going to have a hole in the graph. In other words, 3 is a 0 of the numerator, and 3 is a 0 of the denominator. We could factor this then, since we know that 3 is a 0. I'm going to rewrite my limit here. And whenever you rewrite the function, include the limit in here, because this is a limit problem, so you have to keep rewriting this part of it. In the numerator, we would have x minus 3 times whatever that quadratic factor is over x minus 3. Now, how am I going to figure out what this part is right here? If I take my numerator and I divide it by x minus 3, I'll get whatever's left over. I can use either synthetic division or long division to do that. If I use synthetic division, I have 1, negative 5, 8, negative 6. Bring down the 1. 3 times 1 is 3. Add. Multiply. Add. Multiply. Add. Notice a remainder of 0. I should get a remainder of 0 because I already know that if I plug 3 into this polynomial in the numerator, I get 0. So I know that 3 is a 0. So what's left over in this part of the factorization is x squared minus 2x plus 2. So how could I figure out what the equation of this graph is? Well, divide. When I cancel out the common factor, I get the equation of the parabola. Here's the equation of this parabola. The equation of the parabola minus a value for when x equals 3. So there's a hole in the graph at 3 something. So let's figure out what this limit is. Now, would you agree that if we get close to 3, we're going to get close to this y value? Let's check this out on the graph. If I get close to 3 from either the left-hand or the right-hand direction, so I'm getting closer to 3, what's happening to y? Y is getting closer and closer to whatever that missing point is, whatever that missing y value is. So if we go, that's not what I want. If we go to my graphing calculator and we go to the next graph over, not that one. Where's the one that has the hole? Oh shoot, did I not put that one in there? No problem, I can easily check this one. This one, if I go to my tab and go up to find the equation, this equation, oh, there it is. That's the one I want, actually, right there. Okay, so I'm going to hide this one. Oh, I hid the wrong one. I want to hide this one. And I want the other one to come up. That's the one I want to see. I'm going to pause a moment so I can fix this issue. Thank you. Okay, I'm back. I found this graph now. I want to trace it. Now, if I put in 3, you'll see it's undefined at 3. We can't actually see the hole on this graph. On the 84 you can actually see the hole. Can't see the hole, but I know that it doesn't exist at 3. But what happens if I get close to 3? So let's try 3.1. 5.41. Let's try 2.9. 2.9, 4.61. Okay, let's try 3.01. 5.04. 2.99. 4.96. 3.001. 5.004. 2.999. 4.996. You can see that as I'm getting closer to 3 from both sides of the equation, I'm getting closer to 5. So this fits the definition of a limit. There's a discontinuity, there's a hole, but we say the limit as x goes to 3 is whatever y is getting close to, and it's getting close to 5. Now to illustrate that, if I reduce this function by what this is called eliminating the discontinuity, this is known as a removable discontinuity, so I have removed the discontinuity. And so then I say, I'm going to continue down here, this equals the limit as x goes to 3 of x squared minus 2x plus 2. Well, when I get to that part, I just substitute the 3 in, and I say that's 3 squared minus 2 times 3 plus 2. 9 minus 6 plus 2, that equals 5. There's my limit. That's what I found when I traced the graph. So this is the process we use to remove the discontinuity. You figure out that 3 is a common 0 of both the numerator and the denominator. Therefore, there is a common factor of x minus 3. You divide to find what the other factor of the numerator is, cancel out the common factor, and evaluate the limit again. This is known as evaluating the limit. I plug the 3 back into what's left of my function, and there's my limit. Now, is there an actual point at 3, 5? No. So the graph is discontinuous. There's a hole at point 3.5, but we still say that the limit as x goes to 3 of the function f of x is equal to 5, because it fits the definition that as x gets sufficiently close to 3, y approaches 5, and it approaches it actually from both directions. So this is what's known as a removable discontinuity. This particular process of finding something with a removable discontinuity and learning how to evaluate and find the limit when the actual point doesn't exist is going to be really useful when we start talking about the derivative in calculus on Monday. So this is a technique that we're really going to use a lot.